Okay, so let's see if I can do and explain this one in about 5 minutes. Just part A of 2018 Mech 3, to show how I can do it. And so tomorrow, what I want to do, you'll have some other stuff to work on. Would you like to take in-class AP? Do you want to take a free response quiz I mean, a multiple choice quiz that's like either curved or correctable? Maybe we should vote on that too. You don't care. Correctable is better. You have to. I need some feedback from you. Like, are you ready for a little more stress of a curved quiz? Because you've been doing well so far. You should probably bet on yourself. I think you'll do well. Or are you just so stressed out now, closing out the end? I need a correctable quiz. I don't want to take any risks. You're the student, so it really matters how you feel and how you perceive things. Okay, using integral calculus, so I have to write an integral, show the rotational inertia of the rod is ml squared, 1/2 ml squared, not what it normally is for a rod, which would be 1/3 ml squared. How's that possible? Well, it's weighted toward the end. It's really more like a wedge. Okay, and watch out. So this lambda is its linear density, and what I have to point out is this means that dm for a uniform rod would just be capital M over capital L times dx, right? That means that dm is always just lambda dx. Okay, and wait, whoa. Why do we need dm? That's what I have to say this, or for my due diligence in teaching. It says on the equation sheet that the real rotational inertia is r squared dm. Okay, and that's how you should start this thing using integral calculus. There's an integral, and there's rotational inertia. I better start from that step. Okay, but it's important to know too. So okay, that actually means move my little bar out of the way. dm, nobody wants to do dm. Integrate over mass. That's nuts. We have to do something reasonable. We take 2m over L squared x dx. Okay, there's a bunch of constants times x dx. I can do integrals on x of monomials with x. No problem. Okay, so we're going to show this to get the rotational inertia. So this is basically, and part of, I'm having you do this, part of the one on the test is just can you set up this integral and make a reasonable attempt at it. It's not the wedge, it's a different one. Um, but okay, so I'm going to integrate from x goes to 0. I don't think you really need the x there. And now look out here, where's my mess? I have to do 2m over L squared x. That's part of my dm. I still need my r squared, which is x squared dx. Okay? So it's an x cubed integral. That's probably the first thing we could miss, and I'm sure they'll have some points for not getting the correct answer this time. We can look it up later. So all those constants come out. I'm really integrating x cubed dx, which should be easy by now for you calculus students, from 0 to L. Okay? Yeah, you can do that antiderivative, evaluate it. Okay, we hurry. That's why it will only take me 5 minutes, because I don't have to explain how to do that. Okay. So I've still got my constants, 2m over L squared. I integrate, and I should have L to the 4th power over 4 minus, 0. Okay, and then so I just distribute my stuff. I should have, m L squared over 2. I showed it. Okay, I have the limits on my integral. You can do as many, as long as you're showing, you don't have any substitutions to do, and I factored out my constants just kind of showing off. You're allowed to do as many algebra steps in your head as you want. I set up an integral like they asked. I do need to write down how I define dm, right? On the equation sheet, it says I equals r squared dm. I should put, since I have 5 seconds, I should put that my r there equals x. my lever arm equals the x coordinate in this situation, and dm I wrote up on the other page. So there's x squared, it's r squared. dm is this function that they gave, dx. So I showed how I plugged those in. That's it. I used integral calculus to evaluate that problem. Problem solved. I probably got all the points. Okay. What if they took that weird thing and the axis is not at the end? What would it change if the axis was like a third or a quarter of the way down? We did some homework problems like this from the book. Sure, Ben. You would either, excellent, you would either change these bounds. It could go from like minus a quarter x to 3, or minus a quarter L to 3/4 L if I'm 1/4 down the bar. I think that's a homework problem we did. Just change the bounds of the integral. You could also do this from the end. Oh no, you couldn't. You could do it from the center, from minus L over 2 to plus L over 2, and then parallel axis your way back out to where it wants. But you have to go parallel axis from the center of mass. Ooh. Okay. Don't worry. On the test, I feel like giving you a uniform rod to integrate. So it won't have some weird function. But you'll still have to show the integral as though it's this thing. Okay.